Hi guys, in the last tutorial we discussed about a distributed database and what are the three main reasons of even choosing a distributed database, right? So these are the three main problems we see in real world for which we are choosing a distributed database: scalability, fault tolerance and latency. We can see the same here: scalability, fault tolerance and latency. You can, like, people who are new to this video can refer the old video to understand more about this. Now to solve these three problems, we have two solutions of even using a distributed database. Okay, one is vertical scaling or scaling up, and the other one is horizontal scaling or scaling out. So these are the two ways of you are distributing our data. Okay. Even in vertical scaling, you have two more architectures inside this. One is shared memory architecture, and the other one is shared disk architecture. So in the shared memory architecture, what happens is, let us assume initially you have a single mission in your application. So single mission usually has a single CPU, single RAM, and then a single disk, right? Now your application is not able to scale. That's why what we can do in shared memory architecture is you can add more power to your mission. Since you have a single mission, you can add more power. Adding more power means you increase CPUs. Okay, from 1 to 3 you can increase the CPUs, you can increase the RAM, and you can increase the disks also. So this way what we can use is, since you have increased number of disks, you can store a high volume data now. And since you have increased the CPUs and RAM, what you can do is you can process the data at a higher rate compared to a single CPU, right? So in this way, you can scale your application to a higher load, and even read and write request also you can handle it much better than using a single CPU, right? So this way scalability issue is solved, right? But if you think in a real world scenario, what we expect, let's say your mission, which consists of a single CPU, is handling 10 million requests in a day. Now, if you increase to 3 CPUs, what you assume, what we expect is it should handle thrice the single CPU, right? Which means that thrice 3 into 10 equal to 13 million requests. So ideally what we expect is, since we are tripling the CPU, RAM and disk, our request handling also should multiply by 3. But if you see in the real world, a mission with 3 CPUs doesn't handle 30 million requests, because these are all, we have put 3 CPUs, 3 RAMs and 3 disks on a single mission. You did not segregate the missions on the same mission, you have added more power. So even when you add the more power, let's say one of the CPU is processing, maybe the data that CPU requires might be present in the disk that is far from the CPU. So there are few limitations like this, due to which it cannot scale much. But the cost of buying a CPU, RAM and disk is very high. Though we are putting more cost, it is not scaling to the level we expect. So though, like, we can increase our scalability of our application, but not to the extent we expect. So we don't have here 100% scalability when we went with the shared memory architecture. So this is with respect to scalability. Let's see fault tolerance. Okay. So what we have is, since we have 3 CPUs, if one of the CPU goes down, what we can do is we can swap the CPUs, RAMs or disks, so that we can make our application available to our users 24/7. But even that is also a very limited. You cannot 100% guarantee that your application is highly available by using shared memory architecture. Okay. Now, when it comes to latency, all these are the comes under a single mission. And if you have a single mission, you can put it only at a single place, not at multiple geographical locations. So latency issue is not addressed in shared memory architecture. Let's see a diagram related to shared memory architecture. Now, initially you have a machine. This consists of a single CPU, single RAM, and single disk. Now, since you are adding more power, it's like you add more CPUs. So, vertically scaling. You are scaling it. You are scaling your machine vertically. Okay. Now you have a single CPU. Another one. Now, even if you add one more mission, you add another, even if you add one more CPU, it's like you are adding it on a single mission, right? So that's why it's called vertical scaling. So we saw the drawbacks present in shared memory architecture, right? Scalability is not achieved 100%, even the high availability is also limited, and latency issue is not at all addressed in shared memory architecture. Now let's go with this shared disk architecture. So in shared disk architecture, what happens is, this is the diagram of shared disk architecture. You have a disk that is shared among multiple machines. So you have multiple machines here. CPU and RAM is different for each machine, but the disk that all machines are using is the same. So in this particular architecture, since you have multiple CPUs and multiple machines, so fault tolerance is achieved 100%. Okay. So since you have multiple machines, even if one of the machine goes down, what we can do is other machines are there to handle the load. That's where we can achieve high availability here. Even scalability level also, you have multiple machines, and even you can add more and more disks also, but those are all shared among the machines. But it's not that you should have a single disk here. Here it is represented as single disk, but you can have an array of disks which are shared among these machines. So even scalability is also achieved here. So you can add multiple disks which handles the storage volume. Since you have multiple machines here, these will handle read request and more write request also. So scalability issue is also solved. Coming to latency, we can place these machines at multiple geographical locations. Okay. Since you place machines at multiple geographical locations, users can access the machine which is very close to them, addressing the latency issue. So all issues that we have discussed before are addressed in architecture, shared disk architecture. But there is a limitation here. It is locking and contention. Okay. What is this issue? Let's see here. You have a single disk here, right? You have a disk which is shared among multiple machines. So if you consider a write scenario, let's say in this particular disk, you have a record one which has a value foo. Okay. What these machines does is, whenever it gets a request, it loads the value from the disk and it stores in its local cache, so that it need not request the disk every time, because reading from the disk is a costlier operation, right? So to avoid the overhead, what these machines does is, it requests the data from disk and it loads here in the cache. Okay. Now let us assume a user comes and he wants to update the foo value to bar. Okay. Now, if you just update the disk, you will have the stale entries in all these machines, right? In shared disk architecture, whenever a write happens, along with updating the disk, it updates the cache copies of all these machines. So, while updating the cache copies, it has to obtain a lock. Otherwise, it cannot update it. So, it will acquire the lock to update the cached copies of all these. So you will have an extra overhead when you obtain a lock and update the entries, right? So this contention and the locking is the drawback in shared disk architecture. Now, since we have seen the pros and cons of shared memory architecture and the shared disk architecture, let's go with the horizontal scaling or scaling out. So horizontal scaling or scaling out works on shared nothing architecture. Here you have something shared in the vertical scaling, right? Be it memory or be it disk. But in horizontal scaling, you don't have anything shared. You have multiple missions, like you have a multiple mission like this. Okay, you have multiple missions placed at various geographical locations, and each mission communicates with the other mission at network level, which is at the software side, right? So, in shared nothing architecture, nothing is shared among the missions. Each will have their own tables. Okay. Uh, so, if you see but even in the shared architecture, there are two ways of share. Like, there are two ways how you distribute data on several missions. One is a partitioning, and the other one is replication. So, replication. Now, first we'll talk about replication. Replication is nothing but exact copy, replica. Usually, even in general also, you will see what is mean. You'll usually hear replica, right? Replica is nothing but same copy. Let's say here I have 100 records. Here also I have 100 records, and here as well I have 100 records. So you have a same set of data on each and every mission. So if you see these missions, those behaves like an exact replica of each other. So this is called replication. Copying the same set of data present on a mission to other mission is nothing but replication. So you have same set of data on multiple missions which are placed at several geographical locations. So with this approach, scalability is achieved. You can store high volume of data. Even read and write requests also are shared among multiple missions. Fault tolerance is achieved because there are multiple missions. Even if one of these missions goes down, other missions are there to serve the user traffic. And if it comes to latency, since these are present at multiple data centers of multiple geographical locations, users can request data from a nearest data center, not from the one which is very far from them, right? So all three issues are addressed here. Now, what is mean by a partitioning? Partitioning is like you have 100 records, right? So let's say you have 100 records and you have three missions. On mission one, I store, first mission I store only 35 records. On mission two, I store 35 records. And on the third mission, I will store 30 records. So instead of storing same copy of data on each and every mission, what we do is you split your data and store some part of data on one mission, the other parts on on other missions. So this is called partitioning. So I'll explain both partitioning and replication with the help of a simple diagram. So if you see here, the first part. So first part here, left part is partition 1 and right part is partition 2. Even in partitions, you have replicas also, replica 1 and replica 2. So in the first partition, you have 136, 211 and 377. In the second partition, you have 629, 696 and 858. So you don't have same set of data in partition 1 and in partition 2, right? If you see the replicas present in partitions, you have the same replica of data. So you are partitioning data among multiple partitions, but if you see the replica, you have a same set of copy. So this is the partitioning and replication in the distributed data. In the coming tutorials, we will talk more about shared nothing architecture. It's not because it is one stop solution for all problems we see in database. It's just because you see multiple issues, like a developer has to be aware when he's going with shared nothing architecture. That's why we will discuss multiple trade-offs that are present in shared nothing architecture, that we will discuss in detail in the coming architectures, okay, coming tutorials. Thank you.